I am Amanda. Hi, I'm Bridget. Hi, I'm Alexis. Hi, I'm Mama. Welcome to another episode of
Clean Code.
Clean Code. Your best episode of Derby. To begin a journey in this episode by Uncle Bob. Uncle Bob. Enjoy. Uncle Bob.
Welcome to episode 18. This is the episode about the component case study. You didn't happen to bring a component for me to study, did you? Oh, wonderful. Anyway, do you remember the last episode, episode 17? In that episode, we discussed component coupling. Remember, we began with the morning after syndrome? This is what happens to large teams. They start to step all over each other. And remember, we dealt with that by introducing the acyclic dependencies principle. The acyclic dependencies principle says that components, when they depend upon each other, should not depend in a dependency cycle. After we talked about cycles, we started talking about stability. We defined stability as the impact that one component has upon another as it depends upon it. And we defined a principle, the stable dependencies principle, as saying that components should depend upon each other in the direction of increasing stability. After that, we talked about the stable abstractions principle. You remember that. That was all about the components at the bottom of the dependency graph that were really stable and hard to change. The stable abstractions principle gives us an escape clause from all that stability and rigidity because it puts the components at the bottom of the graph into abstractions where they can conform to the open-closed principle. So, now in this episode, we're going to study how to partition a system into components. And the example we're going to use is the payroll case study from way back in episode 14. Remember that one? When we used all the solid principles to do the class design of payroll? Well, now we're going to break that into components. We're going to use component cohesion and component coupling, and we're going to figure out the best component partitioning for this problem. So I hope you're all packed and ready to go, Because after we study some antimatter and a little bit of CP symmetry breaking, well, then we're going to embark upon a journey of component case study. Ha! In 1898, a well-known British physicist by the name of Franz Arthur Friedrich Schuster published two whimsical letters in the journal Nature. They were meant as jokes. He talked about this mythical substance that he called antimatter. He discussed anti-atoms, anti-solar systems, and even an anti-universe. And he suggested that when antimatter met matter, the two would annihilate. He didn't have any evidence, or not even any kind of theory. He was just joking around. And I guess the moral of that story is, be careful what you joke about. In 1928, Paul Dirac was combining the equations of relativity with quantum mechanics in order to describe electrons that were moving very, very fast. The resultant equations allowed for the existence of an oppositely charged particle that was otherwise identical to an electron. That is, an anti-electron. And by cracky, 4 years later in 1932, Carl Anderson detected one of them little buggers. He called it the positron for positive electron. Since those days, we've come to realize that every particle of matter has a corresponding antiparticle, which has the opposite charge and spin, but is otherwise identical. We've even managed to create and store hundreds of neutral anti-hydrogen atoms for minutes at a time. We keep them in a magnetic bottle. That chap Schuster was bang on right, because when antimatter meets matter, well, it annihilates! Yeah, I mean, consider what happens when a hydrogen atom meets an anti-hydrogen atom. The hydrogen atom is surrounded by a negatively charged cloud of electrons. The anti-hydrogen atom is surrounded by a positively charged cloud of positrons. The two clouds attract each other, and when they meet, the electron and the positron annihilate each other in a furious burst of energy, which leaves the two nuclei exposed. The nucleus of the hydrogen atom is a proton positively charged. The nucleus of the anti-hydrogen atom is an antiproton negatively charged. The two attract each other, and when they combine, they annihilate in a much larger burst of energy. Oh, so like, boom. Yeah, boom. Or rather, bang, Big Bang. Because, you see, we believe that the universe began when equal amounts of matter and antimatter were created and then annihilated each other. Now, of course, that much annihilation would produce an immense amount of energy, and we see that energy. It's all over the sky. It's the cosmic microwave background. That's where all that energy came from. So we can see the results of that mammoth matter-antimatter annihilation in the sky. But that leaves us with an interesting puzzle. Indeed, it does. For of all of that matter and antimatter annihilated, why are we here? Remember the experiment from the previous episode that allowed you to tell which side of the mirror you lived on? Recall that it was the spin of a beta decay neutrino that an experimenter on one side of the mirror would detect as spinning clockwise, but on the other side of the mirror, they detected as spinning counterclockwise? Well, it turns out that if that experimenter on the other side of the mirror happens to live in an antimatter universe, then he would detect the beta decay neutrino spinning clockwise. In other words, the two experimenters would give the same result. There would be no way to tell which side of the mirror either experimenter was on, or even if they were on different sides of the mirror. This symmetry is called charge parity symmetry, or CP symmetry. Indeed, given CP symmetry, an antimatter universe on the other side of the mirror would be absolutely identical to a matter universe on this side of the mirror, and no experiment could determine the difference. So here's the weird bit. In 1980, James Cronin and Val Fitch were goofing around with a particle called a kaon. Now, the kaon is a cool particle because it decays into its own antiparticle, an antikaon. And antikaons decay into kaons, so they kind of just bounce back and forth between the two states. What Cronin and Fitch realized is that the rate at which kaons decay into antikaons is different from the rate at which antikaons decay into kaons. What this means is that an experimenter, by measuring the rates of kaon decay, can determine whether they are living in a matter world on this side of the mirror or an antimatter world on the other side of the mirror. And that means you can tell which side of the mirror you're on, so that their CP symmetry don't work, do it? And so it was that when the matter and antimatter of the early universe underwent the vast convulsion of annihilation, a small asymmetry in the laws of physics allowed a tiny fraction of matter to persist. Us. Do you remember the design of the payroll system from back in episode 14? In this episode, we're going to break that design up into components. But before we begin, let's go get our bearings back and look at that design again.
Oh yeah, we began with the use cases, didn't we?
Yeah, that's right. We applied the single responsibility principle by mapping out the actors and operations for the add employee use case. Then we converted that use case diagram into a class diagram that depicted the classes and data structures that implemented the operations of that use case.
Yeah, but Uncle Bob, I'm a little confused because I thought I heard you say once that you really wouldn't draw those diagrams.
Yeah, that's right. I mean, I drew them for you because in a video like this, it makes it easy for me to communicate my thought process. But in real life, I wouldn't be drawing them anywhere near as formally. Oh, I might go to a whiteboard with the team and scratch a few diagrams on the whiteboard to discuss it, but I'm not going to do some big formal pile of diagrams. That would be hideously wasteful.
Yeah, but, Uncle Bob, if you don't keep those diagrams, where's the design kept?
Here. Yeah, it's important that I don't mislead you here. You're going to see lots and lots of diagrams here, and you might get the idea that you're supposed to draw these diagrams well in advance of the code being written. Illogical. A flawed perspective. Right. So, while the diagrams I'm going to show you can be very useful in helping you partition a system into components, these kind of diagrams aren't drawn early. Typically, if they're drawn at all, they're drawn after a great deal of code has been written.
After all, the component partitioning decisions we are about to make are real decisions, and therefore they had better be made on something just as real, code. I don't want to see you basing your component partitioning decisions on fluffy little diagrams that are little better than castles in the air.
10 years ago, in 2003, I wrote this book, Agile software development principles, patterns, and practices. The payroll case study that we're about to go through was fully documented and implemented in this book, including all the component partitioning decisions. If you read this book, you'll see that I didn't even begin the component level partitioning stuff until I had completely written and tested this application. It all worked before I started dividing it up into components. So the component level decisions I made in here were based on the real world, not castles in the air. The design I used in the book is not quite the same as the design you're going to see here. For example, in the book, I did not use separate data structures for the use case data. I simply included the use case data in the use case objects, which I called transactions. Nowadays, I think externalizing that use case data into data transfer objects is a slightly cleaner solution. You may recall from episode 14 that we talked about quite a few use cases, including add employee, change employee, delete employee, pay all the employees, add time card, add sales receipt, add union service charge. We're going to assume that all these use cases follow the same design, which roughly means that the use case will accept as its input a request data structure and will produce an output in the form of a response data structure. Do you remember way back in episode 7 when we talked about architecture? I called these use case objects interactors. And do you remember what interactors managed? They managed entity objects, business objects. So here are the entities for the payroll design. These are the objects that are controlled by the use case interactors. These are the objects that contain the application-independent business rules. These are the business objects. Right there in the center, there's the employee object, and it holds on to 4 strategy objects. The first strategy object is the pay disposition, which determines where the employee's pay will be sent. The second one is the pay type, and that determines how much the employee will be paid. The third is the pay schedule, which determines when the employee will be paid. And the last is the union membership, which determines how many union dues to deduct from the employee's pay. The derivatives of these strategy classes show us the rather large amount of degrees of freedom that these calculations have. I mean, paychecks can be delivered by mail, they can be held by the paymaster, they can be direct deposited, pay could be hourly, salaried, or commissioned, paychecks could be delivered weekly, monthly, or bi-weekly, and employees could be union members or not. Finally, we see that the hourly employees maintain a list of time cards, the commissioned employees maintain a list of sales receipts, and the union members maintain a list of service charges.
Whoa, man. I mean, can you stop and rewind and play that all back again? Because I'm kind of lost.
Keep up, mister. We're going to need a UI of some kind, and we'll probably assume it's the web. So that means we're going to have a whole bunch of controllers that activate the use case interactors by creating request data structures. And then the use case interactors will drive the views by creating response data structures. Now, back in episode 14, we isolated the use case interactors and the entities from the controllers and the views by creating builders, factories, and presenters. We're going to have a lot of these builders, factories, and presenters to manage here, and we're going to hide them behind interfaces. We're also going to need a database, and if you remember our architecture lesson from episode 7, you know that we need to put that database behind another boundary and access it through another set of interfaces. So, there's our design. Controllers use builders to create request data structures that they pass to interactors that they acquired through factories. The interactors manipulate entities and the database in order to create response data structures. The response data structures are passed into presenters, which create view model data structures, which are then driven into the views. Now, take a look at this diagram. How are we going to partition this into components?
I know. Let's put the controllers and the views in the web component, and the presenters, the factories, and builders in the UI component, and the use cases and the interactors and their data structures in the use cases component, and all the entities and database stuff in the entities component. Yeah, that's right.
Bogus, like there's a cycle between the web and the UI, man. And that's like way uncool. Gosh, I hate to pile on like this, but after all those entities, they're really concrete, aren't they? And all your use cases are depending right on them. I mean, isn't that a violation of the stable abstractions principle?
Oh, and for goodness sake, those use cases are volatile. Customers like to change their minds. And one of the things they like to change most frequently are use case implementations. And yet you've got the web and UI depending on these things that are likely to change for all kinds of different reasons. And that violates the common reuse principle.
Suffice it to say that there's a number of problems with this partitioning. There's more, but we don't need to go into them now because I think the point has been made. So, does anybody else want to give this a try? How would you partition this system into components?
Yeah, like I'm always like a really big believer in model view controller, man, because it's like the way coolest application framework for the web like ever. So I'd probably split it up like this, I'd have the controllers depending on the models, because that's where like all the business rules are. And then the models, I'd make them depend on the views. And that makes this really cool like input process output thing. And like if you do that, then there's no cycles at all.
Do you mean to tell me that you would have every single controller depending on every single use case? And then every use case depending on every single view? Can you see the transitive dependency of the controllers upon the views? Every single controller depending on every single view? This violates so many principles I can't even say them all in a single breath.
Yeah, every time you change the view, you gotta rebuild everything. That really sucks.
Well, I'm sorry to say, but I have to agree, because those views are really concrete, aren't they? And like, everything really depends upon them a lot, don't they? So, isn't that a violation of the stable abstractions principle again?
Yeah, it pretty much looks like all you did was draw some lines on there to give us a rough model view controller split without any cycles. It doesn't appear that you tried to make these components independently deployable. Remember, the whole reason for having a component architecture is independent deployability and independent developability. So, who's next? Who else wants to try and make an independently deployable component architecture?
Oh, I'll go. I had some ideas. First of all, there was an awful lot of red in there, and so I thought a little bit of color would lighten the mood. And
I was disturbed by all those straight lines, so I added some curls. Don't you think they look nice? And then in the end, I put my logo up there in the corner, Danny.net.
Excuse me?
Oh, that'll look really nice on the wall of my wigwam.
All right, so let's start this over. And this time, let's focus on the principles. We'll start with the principles of cohesion. Do you remember this tension diagram? We're going to presume that our project is in the midst of active development. And the best position for an actively developing project is at the bottom of that diagram, as far away from the release-reuse equivalence principle as possible, and as close to the common reuse and common closure principles as possible. We'll begin with the common closure principle. Which ones of these classes change for similar reasons, and which ones are closed against similar kinds of changes? Controllers have a many-to-one relationship with use cases. Each use case can be called by many different controllers. Therefore, there is a locus of change around each controller and the factories, builders, and use case activators that they call.
Okay, sure. But wouldn't the interactors have to change as well? I mean, if the controllers change, the use cases probably have to change too.
But there are many reasons why an interactor might change without affecting its controller. Therefore, the interactor is probably not part of the controller's locus of change, since they are not closed together against the same kinds of changes.
Oh, now, hold on. You're not saying that all the controllers, builders, factories, and use case activators belong in the same component, are you? Because if you are...
No, that ain't the situation at all. A great big component like that would be worse than a barn stacked floor to ceiling with constipated cows. No, I reckon what we're going to do is break them use cases up into families, and then we'll divide all those factories and builders and controllers and use case activators amongst those use case families.
Right. Putting all the controllers into the same component would violate the common reuse principle because it would create a component that has way too much knowledge.
Ja, and the same logic applies to the view model, and the presenter. Because these are all tightly cohesive around the presentation details of the view. And they can all be split based on the use case families.
It should be clear that the builder impulse and the use case requests are highly cohesive since the one builds the other. They're going to change for the same reasons, and so they belong together in the same component, although I'd maintain the use case family split. By the same token, the interactors and the use case responses are highly cohesive, and for the same reason, the one builds the other. I'd include in with them the factory impulse and the use case responders, and of course I'd maintain the family boundaries. Entities have no external dependencies, and so they should be grouped alone. They also fall into families, unrelated to use case families. The entity families are liable to be complex because the structures of the entities are complex. The database gateways are related to the entities, but the entities don't know anything about them. The database gateways are used by the interactors, but are not cohesive with either the interactors or the entities. Therefore, the database gateways belong in their own component, but should be partitioned along the entity family lines.
Yeah, and them there database impulses, they're going to be in their own component too. and they's kin to the database gateway, so they'll be split along the same family lines.
So, now let's look at what we've got. The views all depend upon the interactors, and that's good, because interactors are high-level policy, while views are low-level detail. Interactors depend upon entities. Again, entities, being application independent, are higher level than interactors, which are application dependent. The entities are the highest level concept in the system. They don't depend on anything. Interactors and database implementations depend on them.
And those interactors, why, they're dependent on the controllers. And that's just peachy. Because those controllers are about as low level as the trough I slap my pigs in.
Oh, but Uncle Bob, there's a problem. Look, the controllers depend upon the request builders, but the request builders, they depend upon the controllers. That's a cycle, Uncle Bob, a cycle. Oh, heavens.
Yeah, a cycle. I thought that was bad.
All right, now don't get all hot and bothered. I know this cycle's bad, but look, we're not done yet. All we've done so far are the cohesion principles. We still have to apply the coupling principles, and that's just what we're going to do next. So let's tackle that cycle first. The problem is that we've mixed interfaces with concrete classes. Those controllers are concrete, but everything else is abstract. And if you think about it, that violates the stable abstractions principle. We've actually got several problems like this in the design, and some are worse than others, but this one is particularly bad because it leads to a cycle. I recommend resolving the cycle by splitting the controllers component along the abstract concrete boundary. That's a good idea. That gives us another component named use case boundary, and of course it'll fit into the use case family divisions. Man, that cycle is still there. The request builders are depending on the boundaries and vice versa. Who knew that cycles were so hard to get rid of? Well, they can be, it's true, but this one is not too hard to deal with. All we have to do is move the use case request DTO into the boundary component like so. Oh, okay. Cool. So now let's consider the stable dependencies principle. Are there any components here that ought to be easy to change, that are dependent upon by things that are hard to change? Views should be easy to change, and nothing depends upon them, so there's no violation there.
And them controllers ought to be easy to change too, son. I mean, they're changing all the time anyway. Every time somebody's grandmother discovers rest or soap or some other concerned thing, those controllers are going to be changing. But then there's nobody dependent upon them, so I think that's just fine.
The interactors will have to be changed frequently because they implement application-specific business rules, and those kinds of business rules are usually quite volatile. But the views depend directly upon the interactors, and therefore depend on something volatile. That's likely a problem. Yeah, it probably is. Strictly speaking, the views are less stable than the interactors, but only by a bit. So I think we should break that dependency. We can do that by adding the use case responders and the use case response DTOs to the use case boundaries component.
Oh, would you please clean up that diagram? The shapes are all blurring together and making me quite dizzy.
Indeed, I'm feeling rather ill myself.
Okay. I get your point. I'll clean it up. Shazam! Okay, so now I've got it all reorganized into swim lanes. And if you look closely, you'll see that all of the arrows cross the red lines between the swim lanes going in the same direction. So there can't be any cycles. But let's look at the stability. It's very clear that the unstable controller's views and interactors depend upon the stable use case boundaries. And since the use case boundaries are abstract, well then both the stable dependencies and the stable abstractions principle are happy.
Okay, Uncle Bob. But check out that request builder swim lane. Do all those builder impulse really have to be alone like that? I mean, I'm kind of feeling sorry for him over there.
Yeah, I was looking at that too. Those swim lanes make it pretty clear that the builder implementations could really be moved in with the interactors. So, Shazam! There we go. The builder implementations are in with the interactors. And this makes sense because the interactors really depend very heavily on the format of those user request DTOs that are built by the builders.
Yeah, that looks better, Uncle Bob. But I'm still pretty concerned about all those entities because they still look pretty concrete to me. And there's a lot of incoming dependencies. I mean, don't you think that's still violating the stable abstractions principle, Uncle Bob?
Well, yeah, I think you're right about that. I mean, take a look at those entities. Those entities are actually unstable for a whole bunch of other reasons. I mean, who knows what kinds of fields will be placed into them later or what new application-independent business rules will be added. So, Shazam! There! Now we've put those entities behind a nice abstract interface. But I want you to take a careful look at those entity objects because they're not interfaces, are they? They're abstract classes. And they're abstract classes because some of the methods inside them implement the application-independent business rules, while other methods are abstract, the ones that are the data access methods. Those data access methods are implemented down in the derivative, the entity implementation derivative. And that entity implementation is actually created by the database implementation, and so they might as well go together into the database implementation component.
Cool, really, wow. But, I gotta say that those data transfer objects in the use case boundaries components, they kind of bother me because, aren't they really way concrete?
Yeah, they really are. That's a good point. I suppose we could move them in with the interactors. Shazam! But that creates a cycle between the interactors and the use case boundaries. We don't want that. So, mazash! I think we need to undo it.
Oh, yeah, bummer, man. So, what do we do?
We actually faced this issue back in episode 14 when we were discussing the request builders. And we solved it by having the builder return a degenerate interface, an interface that has no declared methods. So, Shazam! There. That actually works pretty well, doesn't it? Now the interactor can just downcast that degenerate interface to the appropriate physical DTO.
Okay, that's cool. But look, man, there's still one of these data transfer objects left. The use case responses, and it's all green and DTO-y. Man, what are we going to do about that one?
Well, Shazam! There, we'll just use an interface. A nice little interface that provides all the accessor methods that are implemented by the DTO.
So this is looking pretty good. I mean, there's no cycles. We've got a bunch of concrete components that depend upon abstract components. We've got a bunch of unstable components that depend upon stable components. I mean, from a high level, this is looking pretty good.
Okay, Uncle Bob, this is great. But you know what I don't get? I don't get what all these families are. I mean, what are all these families, Uncle Bob?
Ah, yes, the families. Okay, well, let's start with the entities. Here's that diagram we drew of the entities a little bit earlier. Now let's see if we can partition those classes into a set of components.
Yeah, and so here is a very reasonable partitioning. The employee component is primarily abstract and very stable, and all dependencies come inwards towards it. The disposition, membership, pay type, and schedule components are all concrete, and they all depend on the employee component.
Yeah, that's true, Albert, old buddy. But you forgot one thing. You forgot about cohesion, son. You look at that component there, that disposition component. That's full of classes. Those classes ain't used together. They ain't closed together. They ain't nothing together. And if you were to use one of them like the male class, why, you'd have the other two tagging along behind you like coyotes behind a chuck wagon. That's too much knowledge, Albert, too much knowledge. It violates that common reuse principle.
Yeah, he's right about that, and in fact, we could make the same point about all the other components. So, Shazam! We're gonna have to separate them. Now, I know this looks like every class is in its own component, and frankly, a lot of them are, but I want you to take special note of the hourly, commissioned, and member components, because they contain subordinate classes. As time goes by and more features are added to this system, we might expect these components to acquire more such subordinate classes. Anyway, these are the component families for the entities. There's 12 of them, and that's a lot, but, well, this system's got a lot of little options, and each one of those options probably needs its own independently deployable component. So, now let's take a look at the use cases.
And so here we see the use cases from episode 14. We can partition these use cases into families by applying the same principles of cohesion and coupling. Shazam! And now you can see a potential partitioning. We see the CRUD use cases in one family, the add use cases in another family, the pay use case stands alone. I think this is a pretty good split.
Now there you go again, Albert. You done forgot all about cohesion. You look at those add use cases, you think they're all related because they've got add in their name? Son, are you related to everybody named Albert? Course you ain't. Those use cases ain't got nothing to do with each other, Albert. They're all just piled together into that one component, and it's too much knowledge, Albert. Again, it's violating that common reuse principle. Too much knowledge, Albert.
Yeah, he's right again, so Shazam! There we go. All the ads are in their own use cases, and now we've got 5 use case families. So let's pick one of them and let's draw it out. Let's draw all the components out for the add time card use case family.
Well, so here we see the add time card controller, which creates the add time card request and then passes it to the add time card interactor. The add time card interactor invokes the employee gateway to access the employee and time card and hourly entities. And then it builds the add time card response. It passes the add time card response to the add time card responder, which is implemented by the add time card presenter. The add time card presenter builds the add time card view model and then passes it to the add time card view, and that's the whole story.
Now, Albert, I think the wheels in your head are a little bit squeaky today, ain't they? I mean, that was all fine and dandy and everything, but you kind of glossed over all those factories and builders, didn't you? I mean, how many of them factories and builders do you think we got? You remember back in episode 14 how many there were? There was one of each, Albert, just one of each. We didn't have a whole bunch of them, so there's something wrong with that diagram of yours, ain't there?
Right again. And yeah, we did discuss this back in episode 14. And one of the ways we discussed handling it was to make the builders and factories dynamic. So let's try that. Shazam! There. Now we've taken the boundary component and we've split it into a requester and a responder. The requester is not broken down by use case family, but the responder is. Inside the requester, we see the factory and builder. The factory has a make method that takes an argument that tells us which use case interactor to build, and the builder takes an argument that specifies which request to build.
Well, now, son, you went and forgot about something else. Look at them factory and builder interfaces. You only got one of them now, but you got loads of implementations split by use case family. That don't make no sense, son. You're going to have to figure out some way to have one implementation of each. That probably means you're going to need some kind of registration scheme, don't it?
Yeah, that's true. So, Shazam! Alright, so now we've taken the factories and builders and we've made them concrete. We've gotten rid of all the implementations from the interactors components. We've denoted that the factories and builders have to accept registrations, and I imagine those registrations will come from main.
Wow, lots of adjustments and changes, kind of like when I moved in with my girlfriend. Is it always like that, Uncle Bob?
Yeah, it pretty much is. You know, we could keep on tweaking this for a while because there's no such thing as a perfect model, but I think we've done enough. This is pretty good the way it is. There is one thing that disturbs me a little bit, and that is that we wound up with a lot more components than I thought we were going to.
Really? How many?
So, look at this diagram. It shows all the components without any of the classes. There's two singular components, main and requester, and the rest are all split amongst the families. There's 4 components that are split amongst the 5 different use case families, and there's 3 other components that are split amongst the 12 entity families, and that, of course, makes a grand total of 58.
Whoa! That's more than a deck of cards.
Yeah, it is, and that's a bit disturbing. We could decrease the number by merging all the controllers and views together, and that would knock the number down to 49. We could reduce it by a hell of a lot more by just merging all the entities together. But I'm reluctant to do that, because when you merge components together like that, you increase the coupling of the system, and you reduce the independent deployability. I mean, look at the freedom that this current plan gives us. If we want to deploy a system with just the CRUD use cases, we can. If we want to deploy a system with just the salaried employees, we can. These components are like a set of Tinker Toys. They allow us to compose a multitude of different systems without changing the source code, and that's power.
All right, now see here, son. That's just too many components. I'm telling you, when the pigsty gets full, it's time to get in there and slaughter yourself some pigs.
Okay, you're right. As this project matures and we approach deployment, we should probably reduce the component count by popping some of those component families. But not just yet. It's still early, and I'd like to preserve the Tinker Toy nature of this project just a little bit longer.
All right, you've made your point. I see the value in all of these independently deployable components. But what about those metrics from the last episode? I want to see the numbers. Show me the numbers.
Why? I mean, look at the diagram. All these components either have I-metrics of 0 or 1. There's nothing in between. And most of them have A-metrics between 0 and 1 with nothing in between. So what we've got here is a bunch of adults and teenagers. There's really nothing to evaluate here.
Well, what about the requester? That's not a perfectly abstract component now, is it?
Okay, you got me. This one is a little bit strange. The requester has an I-metric of 0, but an A-metric of 0.5. And that means its D-metric is 0.5, and that makes it something of an oddball. And I suppose we could fix this by putting an interface implementation split in there and pulling out a new component. But I'm not sure why I'd do that. I think I'd just rather live with the oddball nature of this component. So anyway, that's the component case study. Fun, huh? So, what'd you think?
We're not
worthy. We're not worthy.
We're not
worthy.
I know.
In any case, in this episode, we saw how to apply the principles of component cohesion and coupling to partition a simple system into an independently deployable component structure. Yeah, and we also learned that keeping this cohesion and coupling thing in balance, that's a mite tricky. Because you get the coupling just right, and you blown the cohesion all to perdition. But then you get the cohesion just right, and suddenly you got cycles, so it's a trick keeping it all just right, ain't it?
The advantages, however, are significant. The ability to compose systems from subsets of independently deployable components is a power that is not lightly to be discarded.
Okay, sure. But do you really do all this upfront planning like that? I mean, it looks like a lot of work.
No, not really. Like I said before, I really don't do this all up front. Usually, I move these classes around between components as the code starts to come together. Moving classes between components is one of the goals of a good refactoring discipline. And with that, I will bid you adieu because, well, the dogs are ready for their walk, and besides, we're done with the case study, and we're also done with the whole series on solid component principles. So what should we talk about next? I mean, we've got a load of topics in the backlog. Remember, there's that advanced test-driven development thing I've been promising you. There's acceptance testing. There's a whole load of design patterns to talk about. There's professionalism. There's functional programming. But I have been promising you that advanced test-driven development episode. So you're not going to want to miss the next exciting episode of Clean Code, episode 19, Advanced Test-Driven Development. Come on, you dogs. Let's get going. Good dogs. Good. Let's go for a walk. It's a heck of an interesting day out here.
Microsoft would make a box that no one knows how to open. You're not allowed to open it if you don't have a license. What is the license code? Good God.
That's the second one you've struggled with. Oh. They have to get fancy.
It's that time again. 7 years, you know. Come here.
Con los terroristas.
They do the Harlem Shake.